So now I'm going to do a quick example on data types. So here I'm in the repository and I've put in the Hello World example. So if we go into Hello Worlds, we can go into the bin folder and, or let's say we'll be in the build folder. We can run CMake to generate, we'll delete that one because it's not valid. We'll run CMake to generate our build files. Namely, it'll generate this make file for us so that we can then run make, and this will actually compile our program, which we'll then find in the bin folder called bar. And so if we look in the bin folder, which I have in this terminal over here, we'll see bar, and if I run bar, I get my hello world output, right? So now we'll just go up to our second one, data types, which we were looking at a minute ago. And if I look at my slides, which I have here, we'll start by looking at sort of like the basics, like the int. Now, so we'll modify my main.c. Now let's delete this and we'll look at the size of our operator, right? Because generally storing something or a data type, the only thing that's really of interest to us with the basic data types is how many bytes they represent or what the range is. And so the range is used by the compiler to sort of know if you're doing something illegal. If you're setting -1 to an unsigned integer, the compiler is going to throw up a warning or maybe an error and say, hey, you're doing something not valid. Now, -1 is a signed integer, so it has some sort of binary representation, but obviously it's going to be drastically different inside of an unsigned. And so we can actually test this. Hopefully my compiler will let me compile it. So we'll say we'll have an integer called a, and we'll say, stick with more classic, and we'll integer of foo, and we'll give it a value, -1, right? And so then we'll do an unsigned integer, and we'll call it bar, and we'll say, I want to set this guy's value to foo, right? Now let's print out our two integers. So we'll print out, we have our unsigned, or our decimal, we have our integer, and then we have our unsigned. So we'll print out foo, and we'll print out bar. Now if we save this, go up to our build. Oh, this is still in Hello World, so we go up to 2 builds. Remove him. We'll make it, and if we run, we'll see here that we've printed out -1, and this makes sense. You know, we've stored -1 in a signed integer, so we can even make it more explicit, and we could even put the keyword in here, signed. So now we know, yes, this is a signed. It can store from, as we saw in the other slides, can store from negative, what have you, whatever an 8-byte value is, to a positive value. And then this is what happens when a -1's binary representation is put into an unsigned integer's storage or data, and the compiler says, okay, cool, this is an unsigned number, so it's going to interpret it, it's going to put the 0 point no longer in the middle of the range, but at the beginning of the range, and this is the number that comes out, right? So this is why signing, or being careful of signing, is important, and this is sort of up to the user. Now, I might be able to, no, it's not going to tell me. So anyway, we'll go now and look at using the size of operator, because this is a really important operator. It can help to sort of show that everything in C is memory, and data types are really useful for telling compilers or programs how much memory, how many bytes we're actually interested in. So we'll leave this one here, and now we'll look at printing the sizes of them. So if we look at, hopefully there's an entry in the manual. There is not. So size of returns, I'm pretty sure the size, like the size data type. So now we'll print f. We'll just do the same one again. So decimal, and then we'll do another decimal. Not decimal, a integer. And then we'll do size of foo, and they should be the same. Bar. Because they're both integers, one of them signed, but they take the same amount of print it. got a typo. Now if we run this, we'll see they're both taking 4 bytes. So I'm running so I have a 32-bit integer on my system. Now, let's look at, for instance, the long type. So we can just print the straight up the size of long. So we can pass in that make. Oh, I just cannot type today. Printf. And we'll see that a long is 8 bytes on my system, right? So that looks at the size of operator and why we should use the size of operator instead of hard coding byte lengths or integer or data type sizes. Now, the other sort of non-basic type that I explained was the enumerated types. And these are very useful for creating code that's very easy to read. So if I wanted to sort of represent the colors of the rainbow, right? I can use an enum, so this is an enumerated type, and I can say rainbow colors, and so I will set them to, let's see, we got like, I don't even know them, so red, blue, I guess, green, purple, yellow. That's enough. So now I have my red, blue, green, purple, and yellow. Usually, actually, you would do these as capitals. So we would, so that sort of as a standard, people know that caps are generally some sort of enum or a define. So red, blue, green, yellow, and purple. Now what I can do is I can create a variable that stores an enum. So I'm going to say I'll create an enum, rainbow colors, and I can call it my favorite, my fave rainbow color is red, right? And then it's really useful for when I want to create a variable or with a certain data type which has a sort of human readable number. So because I haven't actually specified values in here, you can also do this as well by putting in equals 1. Doesn't have to be in order. This can be like 5. Let's make this like 9. And then what I can do is I can print them out, and essentially just the compiler resolves this number to be some sort of an integer value that your code uses. But as far as the program is concerned, it's a human readable like word or something that we can deal with. So I can print this as well. So say like enum val, and then we'll do this, and we'll say the size of an enum as well. So we'll find out that. And so my fave rainbow color and size of we'll go my rainbow enum rainbow colors, and we'll build this and run this. And so you can see here we have 4, so it's 4 bytes. It's a standard integer. So as far as my code is concerned, it's this enum resolved to be an integer value. And here we have a 9 because I've set it equal to red, and I've specified that red should be 9 here. Now if I wasn't to specify this red, the first value I believe is always defaulted to 0. So if we make this now and run this, it will now be 0. And it sort of goes sequentially, because generally you don't actually, or sometimes you do, but you might actually not actually care what the integer value is. You'll use this sort of human readable to do things. So I might have some conditional logic where I'm like, if my favorite color is red, print red's the best color or something, right? So those are the basic types we have. We also have the void type. For instance, here we could say, we'll make a quick function called useless function, takes in void, and and prints I do nothing. Now, because it's a void type, it's saying, it's a void return. It says that it doesn't return anything. We don't need a return statement. You could just put in return, but this doesn't really actually do much. But this is useful, for instance, if you were doing some stuff in logic in your function, you hit a point in your function where you want to return. You want to stop executing the function, then it's useful. But in a function like this, it's very much optional. We don't need it. And the void parameter is saying that this function doesn't take in any parameters. So then we can call this in our main loop, and we'll just say useless function. Because it doesn't have any parameters, we pass in anything. There's nothing in here. And so then we can make this and run this, and we'll see at the end it gets called. That's it, right? So that's what voids, without dealing with void pointers, that's the purpose of void in the C programming language.